Alright, so let's talk a little bit about Chapter 10. Chapter 10 is actually a really, really fun chapter. And Chapter 10 is also, in the real world, Chapter 10 is also an extremely important chapter. If you go on and you take additional stats classes or you want to do anything that involves data, you're going to keep coming back to Chapter 10. And what Chapter 10 talks about is correlation and regression. Now, in this class, we only just touch on regression and correlation. Here at UNCC, there's an entire semester-long class that's completely dedicated to only Chapter 10. Right? So, and even in that class, you still just scratch the surface on it. There are many things that you can say about regression analysis and lots of different kinds of concepts. But first here, we just want to get some basic ideas down. So let's talk about some of those basic ideas and what we're even trying to do with regression analysis. So let's talk a little bit about the overarching concept. Let's say that what we've been doing so far this semester is we've always tried to estimate something based off of a characteristic from a sample, right? So we've always tried to say something about a population, and what we were trying to say about the population, we didn't really know what that value is or that characteristic was, so we went out and we took a sample, and from the sample data, then we try to say something about the population. What we're going to try to do now is slightly different. It's going to say, well, what happens if we don't just know one characteristic about something that we're trying to talk about, but what happens if we know two or more characteristics about something that we're trying to talk about? For example, what happens if we knew the dollar amount of every house in Charlotte, and we also knew how many bedrooms each house had in Charlotte? And you wanted to make some kind of guesstimate on how much a house would be based off of how many bedrooms that it has, right? That's something that happens in the real world all the time, right? Let's say that, somebody comes up to you and goes, oh, you live in Charlotte, that's really cool. How much is like a 3-bedroom house in Charlotte, right? To which you would probably say, well, it just kind of depends on where you live in Charlotte, right? There's a whole lot of different kinds of housing situations in Charlotte. But if you just narrowed it down to like the university city, you could have some guesstimate for how much a house would be worth, right? Obviously, there's a lot of characteristics that go along with the house, the square footage and number of garages and so on and so forth. But let's say that we were simply just looking at how much a house is worth and how many bedrooms it has. Then I think everybody will agree that if you have a 1-bedroom house, chances are it's a pretty small house, so the value of that house is going to be fairly low. If you have a 2-bedroom house, well, here it's definitely going to be worth a little bit more than the 1-bedroom house, and so on and so forth, right? Let's say that there's a 3-bedroom house. Maybe this 3-bedroom house is a really nice 3-bedroom house, so let's say it's somewhere up here. And then you have like some 5-bedroom house, and maybe this 5-bedroom house is a little bit more of a fixer-upper, so maybe it's like somewhere down here. Right? Everybody get the gist of what we're doing? So let's say 6-bedroom house is somewhere up here. Well, the way that I started this off is I said, suppose that we knew all the home prices of all the houses in Charlotte and all the bedrooms of those houses in Charlotte, not just these 5 dots that I have here, but does everybody agree that if we went through here and we did it for all of the houses in Charlotte, we would end up with something that, generally speaking, had some kind of upward trend to it? Right? Does that make sense? All right. Well, in this diagram that I've been drawing up here, one thing I've been purposely leaving out is here, this 4 bedrooms. Right? For 4 bedrooms, I don't have any dots up here. So a real-world situation of this might be, suppose that you're a real estate agent, and you have a whole bunch of houses that you're trying to sell, and these houses have either 1, 2, 3, or 5 or 6 bedrooms in it. But somebody comes up to you and goes, oh, you're a real estate agent? Awesome. Can you help me sell my house? My house has 4 bedrooms in it. And you're just like, wow, I don't know how much I should price your house at. Right? So what you can say is, you can say this. You can say, well, I have a general idea that this should have some kind of upward trend to it. Let me try to find a line that best fits my data. So here I'm gonna eyeball this, and I'm gonna say that this line right here best fits my data. Right, does that make sense? So based off of this line now, you can say, all right, here's the line. I think this line best fits the data. The data is the home prices in Charlotte. Now I can say for a 4-bedroom house, I can bring it up to my line, and now I have a way of pricing out your house. Right? Does this make sense? Well, this concept is exactly what regression analysis is all about. Right? Regression analysis simply just says, hey, you have a set of data, find the line that best fits your data, and you can now use this line to make all kinds of statements about stuff in your data. Right? Does this make sense? All right, so a couple of concepts about this now. This line that we just found right here, this is called our regression line. This regression line is going to actually be really, really, really important to us. And the general form of any line is y is equal to mx plus b. Right? You should know this back from like college algebra or something like that. Y is equal to mx plus b. This is our regression line. So now let me try to bring this formula sheet in here a little bit because, like I said before, these formulas down here, these are our chapter 10 formulas. But as you can probably see, most of the concepts that we're going to be dealing with come back to that regression line, y is equal to mx plus b. And which formula on here looks something like y is equal to mx plus b? Yeah, this one right here, right? If you look at this one, it looks something like y is equal to mx plus b. But now what we're doing is we're saying it's no longer y, now we're calling it y hat, because it has like a little hat on it. We're no longer calling it m, we're calling it beta 1 hat, and we're no longer calling this b, we're calling this beta naught hat. Basically, all that's happening up here is we're changing up the symbols a little bit. Now we're saying it's statistics instead of college algebra. Right? It's still just the exact same concept. All right. So this right here is the equation to our regression line. This is what we're essentially going to boil a lot of this stuff down to. Well, let's take a little bit closer look at this equation right here. Here, if we wanted to find out the slope of our regression line, that would be beta 1 hat. If it says, hey, find the slope of your regression line, you can say, okay, I need to find beta 1 hat, but now how do I calculate out beta 1 hat? That's what it says right here. So if it says, calculate out the slope of your regression line, chances are you're going to have to use this formula right here. Right? But now in that formula, what kind of stuff is it asking you to identify? It has this SSXY and divided by SSXX. So first off, just a little bit of gee whiz knowledge. We're not going to go down into too many details about this here, but that SS stands for the sum of squares. We're going to be summing up squares of stuff. Which, if you look at these formulas above, here we have SSXX, here we have SSXY, and here we have SSYY. We don't need SSYY yet for this formula, but I just want to point out because it's another one of those SS's. So therefore, if you need to calculate out beta 1 hat, and you need those SS's, well, right up here you have those formulas for the SS's. And the only thing that you need to have for those formulas are just X, Y's, and N's. So you guys see how it's a little bit of, anybody know what those dolls are called? You know, like those dolls that you kind of stack together, or you pull them apart, and then all of a sudden there's another doll inside. You know what those are called? I forget what they're called. Russian nesting dolls. Yeah, what is it? Russian nesting dolls, right? Yeah. you open up one, you're like, oh, it has to be the last one, right? And then you're like, no, there's another one. Well, it's kind of like what's going on here. You're like, all right, cool, y is equal to mx plus b. Oh, look, now there's a beta 1 hat. All right, cool, now there's a beta 1 hat. But now inside that beta 1 hat, you have like these SS's, and now inside these SS's, you just keep on going farther and farther down to like, it's like the statistics equivalent of those Russian nesting dolls, right? All right. Is everybody good with seeing how slowly but surely like these formulas are all working together? All right. Same thing if you had to calculate out beta naught hat. Here's the formula for beta naught hat. Here, part of beta naught hat is y bar. It's just the average of your y's, and you also need to already calculate out what beta 1 hat is before you can calculate out beta naught hat. All right. I'm really just trying to point out where some of this stuff is on the formula sheet, right? Like I'm not saying, hey, remember all the stuff that I've mentioned so far. I just want to make sure that everybody's aware of like what these different parts are on the formula sheet. The last thing that I want to point out here, and the next thing that we're actually going to talk about, is this little r. And this little r right here stands for our correlation coefficient. And the way to calculate out our correlation coefficient is again using these sums of squares, these SS things. So it's again just these three SS things up here. But I'm going to take a step aside here, and the same way that I talked about this regression line, I'm also going to talk about this little r, which is our correlation coefficient. So little r is our correlation coefficient. So what does our correlation coefficient mean? Well, one of the things that we want to do here is this. If we're trying to fit a line to our data, right, our regression line, one of the things that we want to know is it a good idea to even fit a straight line to our data, right? How closely are these things in terms of a straight line? Well, if we had data that looked like this, it followed a perfectly straight line, and going from left to right, it was increasing. Here, what we're going to say is that our correlation coefficient is equal to 1. But what happens if our data didn't follow a perfectly straight line? What happens if our data looks something like this? Well, there's a clear upward trend, right? It looks a lot like a line, but it's not quite a perfectly straight line like we had over here before. Right? Is everybody good with this? Here, what we're going to say is that little r, it's really, really close to a straight line, so I'm going to call little r right here 0.9. But now what happens if it starts to look a little bit less like a straight line? Maybe it looks something like here. This is a little bit more like the data that we had up here for our bedroom example. Here we're going to say that maybe this has an R of 0.5. And so on and so forth, all the way to where we get to something like this. Here, that doesn't look like a straight line at all, right? That looks like something that got shot out of a shotgun, right? If it looks like something that got shot out of a shotgun, we're going to say that here, this has an R value of 0. Is everybody good with this so far? I'm going to leave myself a little bit of space right here next to that one. I'm going to continue down here, and I'm going to backtrack later on. I'm going to use up that space. Because what I'm about to do now is exactly what I did up here for the positive R values, and that is this. What happens if we had data that followed a perfectly straight line, but instead of increasing as we go from left to right, it's decreasing as we go from left to right? Here, the R value is simply going to be equal to -1. Does that make sense? And now the next two examples that I'm going to give are the exact same thing. Here we have something that looks a lot like a straight line, but not quite perfectly a straight line. What do you guys think the R value is going to be for this? Yeah, like R, like -0.9 or something like that. You guys get the gist of it? So the highest R value that we can have is 1. The smallest value that we can have for our correlation coefficient is -1. And everything in between. Is everybody good with that? If we have a correlation coefficient of 0, the best way to think about this is that this data is not best described by a straight line. Right? Here, this data right here is not best described by a straight line. However, neither is this data right here. This data right here is also not best described by a straight line, right? Ideally, we'd have like some kind of parabola shape that we would try to fit to this. So therefore, here, we're going to say that this also has a correlation coefficient of 0 because it's not best described by a straight line. Right, does that make sense? You can come up with anything else that you want that's not best described by a straight line. Maybe it's this right here, right? The McDonald's arches. Here, this would also just be 0. All right, everybody get the gist of the big picture of what the correlation coefficient is. All right. So let's try to take this away and from these big picture concepts, and let's actually try to go through some of these examples and apply some of these formulas. And we're going to do that using these examples. Let's go to question number 1. A sample of 11 bears in a certain region was taken to investigate the relationship between length x in centimeters and weight y in kilograms. Lengths range from 121 to 152 centimeters, and the data yielded an R value of 0.71 and an S sub E of 21.75. And I'll get to that, what that is here in just a second. And the regression equation we have here is y hat is equal to negative 148.5 plus 1.736 times x. All right. Question A says, what is the predicted kilogram in weight of a bear whose length is 135 centimeters? So let's think about this here for a second. It's telling us that length is what we're going to use for our x value. It's telling us that weight is what we're going to use for our y value. It's asking us to predict the weight. So it's asking us to predict a y value if the length is 135 centimeters. So if x is equal to 135. All right. If you know that x is equal to 135, what do you think you're going to do to find out what y is equal to? Plug it into our regression equation right here, right? Our regression line equation. So here our regression line equation, this problem, is this y hat. The reason why it's not just y, why it's y hat, is because it's a predicted value. Just like the real estate agent example that I gave where I said, hey, there were no 4-bedroom houses, and you had to determine what a 4-bedroom house was worth. Your predicted value for what that house is worth, that's going to be what y hat is. So here it's just a predicted value of the weights. All right, so let's do it. We have, for A, that x is equal to 135 centimeters. Is everybody good that x is equal to 135 centimeters, not it's x and not y? And our regression equation is y hat is equal to negative 148.5 plus 1.736 times x. It's asking us to find a predicted value for the length, so therefore we're just going to plug in 135 in for x. And if you do this, what do you get? Somebody get a number for this? Cool. Awesome. Somebody else get that too? 85.86. So your predicted weight for a bear that's 135 centimeters is about 85.86 kilograms. All right, everybody good with question A? Let's go on to question B. How does the average weight of a bear change for each additional centimeter in length? How does the weight of a bear change for each additional centimeter in length? What is it asking me for? So we're looking for a bear that goes up in length by 1, right? It says for each additional centimeter in length, what's happening to the weight? So suppose we didn't have a bear that was 135 pounds. Suppose that we had a bear that was 136 pounds. We just went up by a centimeter, right? What would happen to the weight? You didn't plug in 135 right here. You plugged in 136. What would change this number? It would go up by whatever this is right here, right? So everybody good with that? It would go up by 1.735. Well, 1.735 and your y is equal to mx plus b. What is this right here? That's your average. That's your slope, right? So everybody good with this right here? This right here is just slope. So if it's saying, hey, if your x goes up by 1, how much is your y going up by? It's just asking for what the slope is of your regression line, right? So here we would say, as x goes up by 1, y goes up by 1.735. Or as length goes up by 1, weight goes up by 1.735 kilograms. Did I mess that up? Is it 6? Yeah, it is 6. Thank you. I don't know how that 5 turned into a 6, but thank you. This should be 1.736. Awesome. Thanks. So, suppose that this question was a little bit different. Suppose that our regression equation wasn't that it was 1.48.5 plus this. Let's suppose that it was negative 148.5 minus this. Now, as the length of the bear goes up, what's happening to weight? It's going down, right? So therefore, as x goes up by 1, y would go down by 1.736. Does that make sense? So basically what these problems are just asking you for is, what's the slope of the line? Is the slope of the line positive, then it's going to go up. If the slope of the line is negative, it's going to go down. Does that make sense? Any questions about 1A or B? Oh, I'm sorry. So what I was doing here is this. I said, suppose that this thing wasn't a positive. Suppose that we change this positive to a negative. Now, if it's a negative, then this right here would change to down by 1. Does that make sense? But the way that we originally had this, and the way that we have our answer written right here, is that this is positive. So therefore, it's SOPIA. Cool. Oh, so x here is still our length.
Okay, so as the length goes up by
Yeah.
about 1 centimeter, right?
That's right.
Okay.
Weight goes up by 1.736 kilograms.
Okay.
All right. Here's one important thing about this concept, and that's this. This very rarely comes up on the final exam, but they have asked this question before, and it's actually a really, really good question. The thing that we can only do here is this. It says that our length is 135 centimeters. Well, here it says that in the body of the problem, it says that lengths range from 121 to 135 centimeters. So therefore, 135 centimeters is inside this range. Right? Is everybody good with that? Because this x value is inside this range, it's okay for us to use this formula, this regression equation right here. Just like I did before when we were talking about the real estate agent, 4 bedrooms was inside the range of the bedrooms that I had. Right? I had between 1 bedroom and 6 bedrooms. So it was completely okay to use that. If they ask you a question that says something like, for a bear that has a length of 160 centimeters, what will the weight of that bear be? You could technically plug in 160 right here into this formula, and it would spit out a number for you. Right? Does that make sense? But you're not allowed to do that with these regression equations. So you cannot just plug in 160 right here, because that would be outside of the range of our data that we have. This is called extrapolation. You are not allowed to extrapolate your regression equations, your regression lines. Soon after you step outside of these bounds, the probability that your regression equation is accurate declines significantly, very, very quickly. So therefore, we simply just say that we can only use x values in the range of the data that we have. Right? So they have asked a question like this before. I think it's come up once. It's a good question. The only thing that you need to do for this is, and it should be an easy question, the only thing that you need to do is cannot be determined. There's no kind of math or anything that you need to do for that. All right, is everybody good with question number 1? Let's go on to question number 2. Economic theory suggests that quit rate, or quits per 100 employees, and average hourly wage are related. Sample data produced the following statistics. Your x bar was 8.6, y bar is 1.88. Your sum of squares for your xx is 68.82, ssxy is negative 23.88, and ssyyy is 11.324. Now it says calculate out the regression equation. All right. What it wants from us, it wants this equation right here, right? Is everybody good at that? Right there is our regression equation. This one right here. Everybody good at that's our regression equation? So that's what it's asking us to calculate. It says calculate out your regression equation. So let's calculate out our regression equation. I'm going to first copy down the formula for our regression equation. And the formula for our regression equation, so this is 2a, is y hat is equal to beta 1 hat times x plus beta naught hat. So this is what it wants. So first thing that we have to do, right, it's like back in college algebra when it said find the equation of a line, 2 things that you need to do. You need to figure out what the slope of that line was, and you need to find out what the y-intercept was. So here, if we want to look at what the slope of our line is, that's beta 1 hat. So let's try to figure out how to calculate out beta 1 hat. Well, if we want to calculate out beta 1 hat, again, going to our formula sheet, we have to take SSXY divided by SSXX. Right? This is where like the whole Russian nesting dolls comes in. All right. So for beta 1 hat, you need to calculate out SSXY divided by SSXX. Again, the SS is stand for the sum of squares. Well, what is SSXY? It tells us what it is in the problem. It tells us that that is equal to, and let me scroll this down a little bit, that's equal to negative 23.88. And SSXX is equal to 68.82. Right, is everybody good with where these numbers are coming from and where this formula is coming from? Somebody do this arithmetic yet? Awesome. So everybody good with negative 0.347 being our slope? Alright, then the only thing that we still need to know is what our intercept is, and that's beta naught hat. And again, if we want to figure out what beta naught hat is, we're going to take that here to our formula sheet again. And now we're trying to figure out beta naught hat. Alright, is everybody good with this? You guys starting to see the trend? It asks you to find something, you go to the formula sheet, you figure out what the formula is, you figure out the numbers, you just plug in the numbers. Okay. So here we have y bar is equal to beta 1 hat x bar. We just found out that beta naught hat is negative 0.347. What is y bar equal to? Yep, that's just given to us in the problem. And what is x bar equal to? That's also given to us in the problem. If you do this arithmetic, what do you get? What is it? That doesn't seem right. Because you're getting about a third of 9, so there should be about 3. 4. Oh, did you say 4.86? Oh, I'm sorry, I heard you wrong. I thought you said 1.86. Good, 4.86. Everybody good with 4.86? So now we have that here beta naught hat is 4.86 and beta 1 hat is negative 3.47. So if we put these two things together, we get negative 0.347 times x plus 4.86. And that's going to be the equation of our regression line. Part A. Everybody good with part A? Part A. Alright, let's do part B. Part B says to calculate out the coefficient of correlation, which is little r, and also the coefficient of determination, which is not something that we've talked about yet, but that's going to be little r squared. Alright, if we're trying to figure out, and this is something that you should remember, right? You should remember that the coefficient of correlation is equal to r, and that the coefficient of determination is equal to r squared. Sometimes on the final exam, they don't have what's in parentheses right after that. They don't tell you that one is little r and the other one's little r squared. Sometimes the problem literally just says find the coefficient of correlation and the coefficient of determination. And if you don't remember what those two things are, like it's kind of hard to do the problem. All right. But we know that the coefficient of correlation is just little r. How are we going to calculate out little r? Cool. You caught on, right? Like, find it on the formula sheet. Here, this is what it is on the formula sheet. It's like this tongue twister SS soup stuff. And here, where are we going to get the values for these sums of squares? Just from the problem, right? So here we're going to get the SY is negative 23.88. XX is 68.82. And YY is 11.324. Did anybody do this arithmetic yet? Negative 0.8554. All right. So if we needed to calculate out what little r squared is, what do you guys think we're going to do for little r squared? Yeah, so here, if we already know what little r is, all we have to do is just square that. Did anybody square that already? Well, if you already know what this is over here, you don't need to do the whole problem over again. You can just square that. Anybody do this? 0.73. So it should be positive since we're squaring it. But 0.7317 is r squared. And that's our coefficient of determination. All right, so I'm going to spend the last 2 minutes just talking about the big picture concept of what r squared is, and then we'll be done with it. R squared says how much of your phenomenon is explained by x, right? So suppose that we were going back to that real estate example, and suppose that on this real estate example, we found out that our r squared value was something like, I'll just stick with 0.7317, like we had on the next problem. What this would then mean then is that here, this is our x-axis, so this is going to be our x variable. The x variable would describe approximately 73% of the variation in home prices. So how much of your home price is explained by the bedrooms? A little over 70%, right? 73%. That's what R says. So whenever you have a large R value, you're saying, hey, this one thing that I know about is going to tell me a lot about home prices, right? Or whatever else you have. This actually has a lot of applications in the real world because what they use regression analysis for is everything from stock prices to home values to anything that you can really describe by a straight line, any kind of data that you can describe by a straight line. You can calculate out the coefficient of determination, and that coefficient of determination is going to say then how much your independent variables describe your dependent variable, or your x describes your y's. All right, any questions about chapter 10? All right, y'all, that's the semester.